the wheel at that location A, then you will find that there is no relative velocity at that point. So we call it instantaneous center of zero velocity because our wheel momentarily stops. That's why the velocity is absolutely zero. Now, what is the advantage of this concept? The concept is, if I ask you to find a velocity at any location of the wheel, linear velocity I am talking about, the rotational velocity everywhere is the same. And now, if we want to find a velocity at point B, or at point C, or at point D, or at point E, or at point in the midpoint of the wheel G, then we need to use, hey, don't talk. The most important thing is we need to use the relative motion. The velocity at point B equals velocity at point A plus B relative to A. B relative to A. And similarly, we can write velocity at point C equals velocity at point A plus the velocity C relative to A. Similarly, at point D, at point E, and at point G. I have written all the equations here. And now, look at here very carefully. This equation, it is a vector equation, and it is a vector equation, not non-linear. As a result, here two unknown. One is a VB unknown. One is our VB unknown. So therefore, even if we know the velocity at point A, still it is hard for us to find the velocity because there are two parameter unknown, three parameter in our equation. So therefore, we cannot solve easily. So now have a look. If we can show that our at point A no velocity, it means our wheel momentarily stops. If we can show that point A is the instantaneous center of zero velocity, then our life how become easy. Look at that. Then we can write in this vector equation that here our at point A approximate velocity is zero. So we can write our entire VA in all equations approximately zero. Clear to everyone? And look at here again. I did not write equal zero. I said close to zero. So as a result, what happened? Look at there. A vector equation here for VB, VC, VD, VE or VG, doesn't matter. Look at there. All our VA equals 0, and then our VB equals VBA, VC equals VCA, VD equals VDA, and VE equals VEA, and our VG equals VGA. Now look at here. How many of you actually noticed? A complex vector equation now becomes simple linear equation. Is it clear to everyone? Left hand side equal right hand side. Now you don't need to worry about any more vector thing. Look at here. Here the VB equals VBA. That's all. That's all simple. And what is our VBA? VBA equals the rotational velocity of the triangle, of the wheel, the velocity here, that omega, same for everyone, and the distance. For example, we want to find velocity at point B, we just need to know the perpendicular or the shortest, not perpendicular, shortest possible distance from B up to the point where our VA was 0. And we can use, with the ruler straight away, we can measure that in our wheel. So, and the rotational velocity, everywhere is the same, because otherwise we will be twisted. If our rotational velocity at point B is different from our D, then our wheel, one section moving faster than other section. So what will happen? Wheel will be buckled. But we say that our wheel cannot be buckled because they are solid. So it means we are doing reverse engineering. It means our rotational velocity will be everywhere same. And similarly, for our C, from C all the way up to A, the distance we need to find RCIC now. Here, it is called radius of the instantaneous center, the distance, shortest possible distance from the instantaneous center up to the point of interest. That distance is called radius of the instantaneous center, which in short we call RIC. RIC is not the radius of the wheel. It is just distance from the instantaneous center location where, in which point we want to find the velocity. So our instantaneous center here for all points. So when we want to find at point B, we need to find from B how far our A. When we want to find at C, from C how far our A. And then when we go at D, how far our A from there. And from E, how far our A from E. And similarly from the mesh center of the wheel to that point. Clear to everyone? So only thing varies the distance. How far away that point from the zero velocity center. Clear to everyone? And that makes our life significantly easy. Now here, one of the important thing. I put you all this particular slide or something you already learned in your engineering dynamics. Now look at here very carefully. Here, velocity general formula using radius of the instantaneous center. V, the linear velocity equals the rotational velocity times the RIC. Times the RIC, radius of the instantaneous center. And in our case, it's very clear. And another important thing, this linear velocity is always 90-degree angle to RIC, radius of the instantaneous center. So here, if you know the radius of the instantaneous center, then you can show the velocity direction. Clear to everyone? It will be 90-degree angle. So that's why I wrote here, V is always 90-degree angle to the radius of the instantaneous center. And that's all. You don't need to remember a lot of things. The only problem is in this equation, in these equations, our life is significantly easier. Why? Because we can find RBIC, RCIC. So now it is not a relative distance, young people. It is just to show you which location we are taking. Clear to everyone? This E, B, C, D, E, G, we are showing that which location. It is so when we take BRIC, it means we are talking about this distance from B up to that point. Clear to everyone? So it is not a relative distance. It is just absolute distance, but we show it which in relation to which point we are taking. That's it. And now you can clearly see, young people, we did a very important thing. What we did? If we can show at point A our velocity is 0, then our complex vector equation become linear equation. And that makes a significant step ahead in terms of solution of a complex problem. That's the one thing. Second thing is, we only need to know the point that we want to find velocity. That point, how far away from the center of zero velocity. That's all. That means distance. And that distance you can see for B is that distance, for C is that distance, for D is that distance, for E is that distance. And when we come to A, our distance is 0. And now, in this problem, in these things, only issue is how to find this. Our wheel is very easy, no problem. But in our mechanism, very often, we do not know where is our instantaneous center and how to find the distance. If we can find the distance, our problem is only 1 minute problem. So, this radius of the instantaneous center to find, first of all, zero center, and second thing is how big this RIC. We can use two different methods. One method we call analytical method, and another method is called graphical method. In this course that you are doing, mechanics of machines course, our objective is to find this RIC by graphical method. By analytical method, you briefly learned in your engineering dynamics course when you did when we started this arithmetic program. Because at the time we did two courses, I think. Engineering dynamics and also mechanics of fluids and solids too. So, at that course, you learn how to find analytically this RIC. And as you did a long time ago, and instantaneous center of zero velocity concept is little bit difficult or hard, I would say. Not a lot hard. Because you are not familiar with it before. So that's why it's a little bit harder. Other things you already have a little bit of familiar. Kinematic things a little bit familiar from your high school physics. But here, no. So that's why the concept is new. I show you briefly how we find the analytical one to give you a little bit of brush up. And then you will realize how easy to find the radius of the instantaneous center of zero velocity by graphical method. Because if you do not understand the analytical one, it is a little bit harder to visualize what's going on in graphical method. Why we need to graphical method? Because in graphical method, when we links have a lot of links, 4 bar, 6 bar, 7, 8 bar, 9 bar, 20 bar linkage mechanism, at that time, by analytical method, it will make you mad. Too many things you need to do. But graphical method much easier, quicker. That's why we are focusing in our course, graphical. So let's go to have a look. Let's go. Oh, before I move on to. Now look at here very carefully. Hey, every time when I go point B, I'm showing our BB is a 90-degree angle to this radius. And when at point C, I'm showing the BC is a 90-degree angle of our RCIC. And when I'm going to D, our velocity BD is a 90-degree angle of our RDIC, that distance. And when we are coming here at point E, our velocity is perpendicular to the REIC. But when I come here, our radius is 0, therefore our velocity becomes 0. So now look at very carefully. Where we can get the maximum magnitude of the velocity among these 5 of them? Anyone can tell me? Where is the highest velocity? At point C. At point C. Why? Because the distance at point C is the highest. The rotational velocity everywhere is the same. It doesn't change. The magnitude, the velocity, linear velocity magnitude will change how far that point is from A. That's it. Simple thing to remember. How far that point is from the center of zero velocity. And our center of zero velocity is here. And now have a look. What happens? If we look at there, if you consider my point B is on this side, so you go here, velocity increases, linear velocity increases, and highest is at the point C, and then you come back, it is reducing, and then when it comes to point A, velocity becomes 0. Can you see how wheel is rotating? And then when it is coming to the contact point, velocity becomes, the linear velocity at that location becomes 0. So that's the visualization, like a little rosette, like a rosette. Okay. All right, now let's go to C. Anyone can tell me what is the velocity will be at the midpoint, the center G? At point G. 0 cannot be, because there is still rotational velocity there and distance is there. From G to A, you have half of the diameter. So it is a half of the velocity of BC. So that's why if you draw, look at here. Hey, I'm not sure how many of you actually noticed. Look at there, how I did. Because that is the entire radius. Even when we are G, our RGIC, what is our RGIC? Yeah, RGIC is actually half of from here up to that distance, correct? The velocity our VG will be still perpendicular to that line, but it will be half. So if you draw a limit line from here all the way up to that point, and you can see at every location velocity will be increasing because your RIC increases at that point is the maximum. So when you are at the midpoint, it will be half of your BC. Half of your BC. Look at there. Look at there. When at point C, you have the entire diameter of the wheel. And when you are G, you become now R, D by 2. Your RGIC is a D by 2. Diameter by 2. It means another word, radius. Alright. So there are 4 ways you can find the radius of the instantaneous center analytically. Four different ways. All problem will be fitting within that 4. Whatever the issue is, it will fit within that 4. And then, and yesterday remember I told you, the instantaneous center of zero velocity method is only valid for rotational motion or general trail motion, not translational motion. And I also show you why. You see here in a second. So now, when a linear velocity VA and the rotational velocity of the object is given, and now, so by formula, so this is our rigid body. This is our rigid body. The VA is given this one, magnitude, whatever it is, 2 meters per second, 4 meters per second, or 20 meters per second is given. And the rotational velocity also given. It is rotating anti-clockwise. Say rotational velocity is 2 radian per second, for example. So it means it's given. So now we need to find what is the radius of the instantaneous center. How far it is. What is the length of it. So we write here our formula. The VA, this VA equals omega times RAIC. and from there we find our RAIC equals VA by omega. So if say our VA equals 2 meter per second and our omega equals 1 radian per second, so our RAIC will be 2 meter. RAIC will be 2 meter. Now, how our RAIC is directed? It will be 90 degree angle, 90 degree angle on this our VA, and our VA root is here. From here is our VA is located here. From here, this is going the direction. So therefore, we draw a line perpendicular to our VA, which is I am showing you 90 degree angle, and then this 2 meter per second, which I say, it is 2 meter or whatever it is, based on your, it will be from here on that direction 2 meter, or from there up to that point it will be 2 meter, because if one radius of the instantaneous center, it can be mirror image both sides. It can be mirror image. So therefore, from here up to that point, that is our RAIC. Generally, if it is given. And then the second scenario. Second scenario is the two velocities are given in the rigid body, our VA and VB. VA and VB. So our VA is this one, is our VA, and our VB is acting on that. So it's clearly we can see on the rigid body, our VA and VB are going to different direction. So therefore, it is a general plane motion. It is not a pure rotational motion. It is not a pure rotational motion. It is a general plane motion. Complex motion is going on. So now, as per principle, the radius of the instantaneous center of RAIC for velocity A will be 90 degree angle. 90 degree angle. So I am not sure whether it is going this way or it is going this way. I draw a dotted line. Look at it very carefully. I draw a dotted line. As per our formula, we said radius is perpendicular to the velocity. We know the direction of the velocity, so it means our radius will be 90 degree angle of it. So what I did, I draw a dotted line passing through it. I know that our RAIC will be on this line, either on that side or somewhere. But it will be on that line. That's the one thing I'm 100% sure. And then I move on to our velocity VV, and the velocity VV is this one. So therefore, RBIC will be a dotted line, 90 degree angle to VB. So I am at the root of our VB. I draw a dotted line, the green dotted line on both sides, and then I can see these two dotted line intersects at that point. So that point we call combined IC for both velocity A and B. Combined IC for both velocity A and I. And again I am trying you, because instantaneous center is a difficult concept. Please try to understand it. Do not try to ignore it. Because if you ignore it, you will unfortunately will be falling behind in terms of knowledge. So therefore, from here, look at it. From there up to point B, that will be our RBIC. From the combined instantaneous center where they are, from there all the way up to that point, that will be our RAIC. In most cases, what you do in real engineering, they will be filling with this scenario. With this scenario. And then, number 3, when two velocities, VA and VB, are given, they are parallel, same direction, but not the same magnitude. They are parallel, VA is given here and VB is given here. They are parallel, same direction, but not the same magnitude. It means both velocity cannot be the same value. It cannot be 2 meter per second, 2 meter per second, or 1 meter per second, 1 meter per second, cannot be. It can be either one is bigger, another one is smaller, but they are the same direction, parallel. Same direction, parallel. So I draw a rigid body here. Our VA is this way, our BB is that blue, the green one, and then unfortunately when I draw a line, and that line is passing through both velocity, you can see. So it means on this line, which is a 90 degree angle to VA, 90 degree angle to VB, our velocity, our radius of the instantaneous center will be on this line for both velocities. Because they are, our radius cannot be somewhere else, because it should be 90 degree angle to the respective velocity. And now the question is, where is it? We know it is on that line, but where? It is somewhere here, somewhere here, somewhere there, somewhere there, somewhere here, or somewhere here. So how can we find it? Then what do? We take a line connecting the edge, connecting the tip of the both velocities. And so a line I draw connecting this straight line, it is not a curved line, the tip of VA and tip of VB, where this line intersects with our radius of instantaneous center line, and that intersection point is called combined instantaneous center for both velocity. Combined instantaneous center. So what I did, I tried to, because our radius of the instantaneous center will be on this line somewhere, because that line is 90-degree angle for both velocities, as per our concept that I explained to you previous slide. So what I did, I draw another line, look at here, another line connecting the tip of this VB and VA, straight line. And this line, where it intersects with our radius of the instantaneous center line, that we call combined instantaneous center of zero velocity for both velocity. And then radius of the instantaneous center. Radius of the instantaneous center, it means from there, where is our B? That will be our RBIC. And from IC up to the point A, that distance will be our RAIC. That's all. And now, young people, why I said that our VA, when they are parallel, same direction, why VA cannot be equals VB? Remember I said that two velocities are parallel, same direction, but unfortunately they cannot be same magnitude. Why I said it? But in real life, it can be. Same direction, same value, it can be. If it happens, what happens? Look at here. That's why I draw that one. So now look at here. If you consider that our VA equals 3 meters per second, and our VB also 3 meters per second, they are parallel. So what I did, I draw a line, 90-degree angle to our VA, 90-degree angle to our VB. So our radius of the instantaneous center that we found here, these things will be on this line. But how I found the combined instantaneous center? I draw a line connecting the tip of BA and BB, right? That actually intersected. But when these two velocities are parallel, this line and this line will intersect. Yes or no? No. And where it happens? In real life? Just to visualize, because I told that things you in the first day. Where it happens? When in a rigid body, all the velocities at any locations will have the same magnitude, same direction. When? Exactly. Only in the translational motion. It means you are moving. Look me. All my parts of body is moving with the same magnitude of the velocity. Otherwise, if this part is moving faster and this part is slower, I will be rotating. It means I am moving this way. Curvilinear path. If this part, this section of my body is moving faster than this part, then I will be moving like that. General concept, young people. Nothing to memorize. Your life, your example is a real life. So, it means it has a pure, if the magnitude are same, these both velocities are exactly the same, they are moving parallelly like that. But in our case, we can clearly see our object is moving this way. Dynamics is not a memorization. Dynamics is pure visualization. In front of you, you see what's going on. If some people cannot teach you that way, they should not be in dynamics class to teach you. As simple as it is. They are the wrong profession, they have to teach other subject. Is it clear? Pure visualization. And now have a look. Hey, young people. You also saw on the other day, on the straight line path, in the straight line path, just 1 second, where is all these things? In the straight line path, remember I show you on the first day, hey, look at here, a curvilinear path, and then it points to the straight line path. And that section, what I showed you here, that section, I said the rho equals what? Radius of curvature. Anyone remember? Infinity. You said rho equals infinity.
0.
Correct or not? And that's why our an, the v square divided by rho and v square divided by infinity equals 0. We wrote it here, right? And what I said, why rho is infinity? Because it is looks like a straight line, but in real life it is not. We don't know where is the curvature goes far away, right? Hey, young people, here, look at there. This line may intersect with this line at an infinity distance. We do have no clue where it is in our planet or another galaxy or Milky Way. We have no idea. Okay, those who don't know what is Milky Way, you can look at it at Google. Later on, but not now. So we have no idea. Look at here, this line can intersect with this line or not. That's why what is the radius of our instantaneous center for a translational motion? We say our line will go far down, far up, another planet, another way, another Milky Way, or whatever it is. We don't know where solar system is. And that's why we say when translational motion, radius of the instantaneous center or radius of curvature, in another word, is at infinity. Clear to everyone? Everything should come together. Everything should come together. Concept is very clear. All right, and now we move on to the last one. Last one, number four. So when two velocities are given, they are parallel but opposite direction. Clear to everyone? This time, two velocities are not in the same direction. They are opposite direction. But when they are opposite direction, they can be equals, they cannot be equal. It means they can have difference. Clear? They can be also equal as well. Let's go to have a look our last one. This is only the four-way. Analytically, you can find the radius of the instantaneous center. There is no other way. Number four. Number four. Look at here. Our rigid body, our VA, is going to the right, and our VB is going to the left, and we draw a line perpendicular to both velocities, and therefore our radius of the instantaneous center will be on this line somewhere, and combined instantaneous center will be on this line. So what we did? We draw a line connecting the tip of both velocities, and where this line intersect with our radius of the instantaneous center line, and that will be our combined instantaneous center. And from here up to point B will be our RBIC, and from here up to point A will be our RAIC. From here up to that point. Clear to everyone? And now have a look. Hey, young people. If our VA equals a VB, say this one is a 3 meter per second, this one is a 3 meter per second. What will happen here? Oh, sorry, this one, we always this one exactly. This one is our, what I said, the VA and VB. I showed you different velocity here. So that's why the instantaneous center is not exactly at the midpoint of between B and A. Clear to everyone? But if the velocity VA and VB are exactly the same magnitude, like this figure, that IC will be at the midpoint here. Clear? And now imagine what sort of motion it is. Look at here. If my body is here, and this section of my body, consider that is my center. Correct? And from here, I put the velocity VA 3 meter is going this way. And this velocity I did not put that way, I put my backward. Clear everyone? So this will move this way and other one will be backing. So what I will be doing? I will be rotating in the same location. So it's a pure rotational motion in relation to mass center, instantaneous center of zero velocity. Clear? There is a rotational motion there. But if you are standing at that point, you will not have any velocity, linear velocity. You will be just rotating like that. If you are standing there. So it means physically you are not moving left, right? Physically you are not moving left or forward or backward. You will be only rotating with the rotational velocity at the instantaneous center of zero velocity. Because we said zero velocity, linear velocity. We did not say rotational velocity. Is it clear to everyone? And this is how you will be finding analytically the radius of the instantaneous center. At any situation that you experience, it will fit within one of these four. Within one of these four. Let's go to do one example. Let's go to do one example. Why we need to do graphical method? Have a look. Hey, have a look at this. Young people. This is our crank connected piston mechanism. We did same problem with the graphical method for the day before yesterday, right? Look at here. Our VA is given, and the physical dimensions are given. The angle are given, connecting rod and the crank. The crank is 45 degree with the horizontal. Crank is 30 degree, and we need to find what is the velocity at point B, piston B. We did by graphical method on our first day. So now, how can we do it? Have a look. Now, look at very carefully. Our velocity VA is a 90 degree angle of OA, correct? And when our VA is going downward, our piston B will be going to the right, correct or not? So if we know the direction of the two velocities, can we find the combined instantaneous center and the radius of the instantaneous center for each of them? We can. Which one? Look at there, which one it fits. Which one it fits? Number 2. Number 2. The two velocities are given. They are different direction, and we need to find combined instantaneous center and the respective radius of the instantaneous center. Correct? Look at there. Our one velocity is going this way. Another velocity is going this way. We need to find combined radius of the instantaneous center. So what are we doing? Let's go to the start from first. This one. If the velocity is going this way, our radius of the instantaneous center will be 90 degree angle of this velocity, correct? So I draw a dotted line. And then this velocity is going this way, 90 degree angle to our OA. So therefore, I draw another line which will be parallel to OA and passing through this way, where this two dotted line intersects. That is our combined instantaneous center. And from there up to that point, it will be RBIC. And from here up to that point, that distance will be RAIC. Correct? And now, did we solve our problem? Not yet. Why? Because now using an instantaneous center, we have to write RVA, the velocity VA, equals omega RAIC, and BV omega RBIC. Now we need to, in order to find our velocity BV, first of all, we need to know what is our RAIC, RBIC. We determine where it is. So we need to now, need to find it. So 2A you can find, 2A. Because our objective is to find analytically, not graphically. Graphically our life is easy. So analytically to find it, to distance from here to here, it is a little bit of challenging. How? Because look at there. We need to, this is our 30 degree, and that one will be on, it is a triangle, ABIC, it is a triangle. So therefore, if this angle is a 30 degree, that angle will be 60 degree, correct? 90 minus 60. And then this angle will be, this one will be 30 degree, look at that, this one is 30, and then this 45 and this 45, total 30 and 45 will be 75. And then 75 plus 60, you subtract from the total three angle of a triangle in Singapore. I believe there is a 180, or it is a little bit less or more. Same? Okay, same. Okay, good. I thought that maybe in Singapore, you have a lot of high-rise building. Maybe you say, we make it a little bit more. So it's 181. No, all over the world is same. All right, so from 180, you subtract the 75 and 60, it will be 45. And now we solve the problem. Hey, have we solved the problem? Yes or no? This young man said no. Why? Why we could not solve it? Yeah, we found the angle. the main thing is coming here. Main thing is coming here. And you found the angle. It does not solve your problem yet. Because unless you find RAIC, that real distance, you cannot do anything. So what do you need to do? You need to do this one. A triangle. A triangle. And young people, you did in high school. A triangle, when this angle is called A, and opposite of the angle A, this arm, it is called A. And opposite, like look at how I do. If you remember that way, if you do this way, which I do and how I say, then you will remember until you die. But after your death, nobody will ask you whether you know math or not. So now have a look. And if this angle is a B, opposite of this angle, that will be your little b, this one. And this angle is C, opposite of this one is C. And now I can write beautiful two law, sine law and cos law. The sine law is A by this A divided by that angle, sine A, and B by sine B, and C by sine of angle C. That is called sine law. Anyone can remember cos law? There are two laws. Anyone remember cos law? No? This is called sine law. We use that one. Quick. Anyone remember? Not forgot. Tell me truth. As I said, if you say I forgot, I believe it more. The reason is I am also like you. I also forget.
Divided by cos.
Huh? Yes.
A divided by cos.
No A divided by B. The cos law, I am writing it for you. You don't need to memorize because you may forget. Just I am writing for you. But it is all related to the triangle. Mother of my equation, this law, that thing is correctly you need to know. Otherwise, you will be doing everything wrong. Clear to everyone? So now have a look. The cos law. The cos law. You don't need to. We are not going to use cos law. You don't need to memorize. But I am just writing it. That's out of curiosity. Now, where is the pen? Here. Cos law. Have a look. Cos law. Cos law or cosine law. Cos law. It is A square equal B square plus C square minus 2BC cos of angle A, and B square equals, I am explaining to you how to remember. B square equals A square plus C square minus 2AC cos of angle B, and then C square equals A square plus B square minus 2AB cos of angle capital C. Now remember how I show you. Look, I am an old man. I remember these things very clearly as I did from high school. Now look at here. When you do that one, the other two sides will be here. Look at how you remember, like a telephone number. Do not try to remember other way, otherwise forget. When you write A square, how many other two sides left of the triangle? Two sides. That will be here. And then minus these two, you need to find two for everyone. And then you put these two again here, BC. And then cos of that angle. Okay? Of that arm, which is opposite of that arm is A. Exactly the same way I do. I never try to remember any formula like arbitrarily. I try to remember formula as a telephone number with a pause. Because if I ask you in your Singapore all telephone number, I think 8 digit, right? And if I ask you, tell me all 8 digit at a time. Can you tell me? No. What do? You pause. First 4 digit, next 4 digit, or first 3 digit, next 3 digit, or 2 digit. You say in sequence. That's exactly Firoz Alam is doing. That's why all this formula in his head. Okay? And do you think that I am using that formula every day? No. But I remember it. Alright? Now, young people, we are not here to test these things. I was saying that something some of the formula, unfortunately, as an engineer, we always need to remember. They are not going away from our head. We need to utilize many, many times. And if you look for this every formula in the book, a simple formula that you're supposed to remember all the time, and your fellow people will not be very happy, and they will not be very confident in you. Okay, so this is why few things, not everything, some basic sum, which you need every time. This formula you try to remember, but how you remember? Do not try to remember very arbitrarily. You'll forget and you'll confused. So for that sine law and cos law, first I draw this thing correctly. I wrote angle A, B, and C. So opposite of angle C will be that arm will be small c, and opposite of A will be that side will be small a, and then opposite of B angle will be that side AC, it will be capital A, small b here. Clear to everyone? Small b, it means the length. Clear? That's all. And then you set up the equation, you're like this. You'll not forget. Okay, so now come back this one. Using our sine law, we can find RAIC and RBIC. We solve our problem? Hey young people, did you solve our problem? You are not saying anything. Quick, we need to move. Did you solve our problem? Our problem was to find the velocity at point B. We only found RAIC and RBIC. But actually, because I wrote in PowerPoint, that's why I put it here. But actually, when I do in the class, I write this formula this way. Have a look very carefully. The VA equals omega RAIC. That's how I write. And BB equals omega RBIC. And now, which omega will be taking? We have a 2 omega. We have omega AB, which is our omega 2. Oh, sorry, omega AB is omega 3, omega AB. And we have a omega OA, which is our omega 2. Which omega will be here? I did not mention here because our two links are moving, has a rotational motion. Our OA has a rotational motion. Our AB also has a rotational motion. Remember in relation to A, I showed you. So my question to you, which rotational motion will be taking here? Rotational motion of our OA, the crank, or we have to take the rotational motion of the connecting rod AB. That is my question. Because I did not define it. I wrote it omega. But formula wise correct, I wrote. That's the formula I wrote for you. Look at there. In the previous slide. This is omega IC. Can you see that? Only I adapted BA, I wrote RAIC. BB, RBIC. That's the thing. Omega is still the same. Clear to everyone? So why I do it? So that you understand the concept. No memorization. Memorization you forget. After sometimes you will not be able to remember. And it will also create confusion. And I don't want our engineers to have a confusion. Very crystal clear. So my question is, now which omega will be taking? And AB. Why, young man, AB? Because every decision we take, we need to justify why we are taking that decision. Otherwise, you say AB, and the other person, no, AB is a little bit far away, I take OA, 2. Then how can I say, you are wrong, you are right? Or you are right, wrong, other person is right. We need to have a justification. Now, look at here. Not written in the book. At least your books, I don't know. Because I did not use, when I learned dynamics, I did not use any English book. Because every word I am telling to you, I am translating from Russian to English and then I am saying you with the speed of light in my brain. Every word and every terminology. Because my undergraduate and masters I did not do in English medium. I did everything 100% Russian medium. Books, studying from book, lecture, speaking, writing, examination, everything. Okay, explain to you. Now, young people, what you do? You stand. This is the way to remember. I want you to have in-depth understanding. Look at here. You stand here at IC at that point. You stand here. Say I am standing or you stand, doesn't matter. I stand. I am at the moment standing at IC point here. Clear to everyone? And I am now looking. Here is our point A and here is my point B. You are looking from here. When you look forward, you can see A, you can see B. Clear to everyone? In front of you, you can see these 2 points. Yes or no? You can see. So now, when I look at point A, look at point B, in front of me, which link I can see? Can I see OA? Young people? No. If I look at OA, it will be only one dot. Because our OA is my line of eyesight. So if I focus this way, it will give me a little dot. I cannot see the entire OA. Correct? I can only see in front of me is our AB. That's why you will be taking only rotational velocity of the link that you can see from the IC point. From the IC point, you need to take the rotational velocity of the link that you can see. You can see only AB because our piston is undergoing translational motion. Its radius is at infinity, so we don't need to worry about that. Clear to everyone? So now, here I have written for you. Now I am writing different color. Can you see that? Omega AB, omega AB. Because we can only see this link from combined instantaneous center. And we solve our problem? Not yet. Because still we don't know what is our omega AB. And then on the other side, young people, on the other side, our VA, so we wrote here AB, and this one we found, and we also identified our omega AB. If we now find omega AB, we can find all the velocity, correct or not? But on the other hand, we know omega, our VA equals omega 2 ROA, correct or not? And from there we find our omega 2, which is our omega. Look at here. From here, we go to our here, and from there we find this parameter, we plug in here, equals, and then from here, only parameter you don't know, omega AB, and you plug in here, and you find the velocity BB. That's all. And now, young people, have a look. Using radius of the instantaneous center analytically to find the velocity at point B, what we did? We look for every possible thing that we learned in the previous life, or not previous life, early life. We need to use our sine law. We need to use our cos law. If I forgot my sine law, I am already grounded, I cannot go anywhere. Is it a good thing? Only 4 bar linkage mechanism. 3 parts are moving. Crank, connecting rod and piston. And if you have a 6 bar linkage mechanism like your assignment, where 5 links are moving, your life will be hell. You need to know not only sine and cos law, you need to know even more in-depth maths. Is it a good thing? No. And that's why the rescue is coming, your graphical method. Graphical way of finding the radius of the instantaneous center of zero velocity that you did in your assignment. Now we'll be talking about that. It's clear to everyone? So it is not a very good analytical way. For a simpler problem, it's still okay, but complex problem, no. And even for a simpler problem, still you need to know your sine law, cos law, and all the geometry and all the trigonometric function that very often we forget. Not only you, I also forget. Many people forget. And forgetting is the is the right way, because people, as with the age, I told you, you will be memorizing, power will be going down. Okay? So how can we solve it? That's why we need to go a new method, the method which allow us not to use any complex math at all. Absolutely none. Absolutely none. And that method you call this one. This one. This method. And what is it? In this method, graphical way to find the radius of the instantaneous center and to find the velocity. Fundamentally, this method based on one principle, and that principle we call Kennedy's principle. Kennedy's principle. Kennedy's principle has the three parts or three sections: part A, part B, and part C. I'm not sure what I have written here. Oh, I've written 1, 2, 3. Doesn't matter. It's the same thing. Any way you can say. But Kennedy did not mention exactly part A or part B or part C or part 1, part 2, part C. But he says sequentially. But I put it separately. Clear to everyone? So first thing, Kennedy said that whenever you see a linkage mechanism, to know exactly how many instantaneous center that mechanism has, you have to use his a very tiny small formula. And that formula he wrote, which I have written there, C equals n times n minus 1 divided by 2. N is the number of links, and C is the number of instantaneous center. Clear to everyone? You use that one in your assignment. Yes or no? Okay. So that we call Kennedy's theorem part 1. In order to determine how many instantaneous center we have in a mechanism, we use Kennedy's theorem part 1 or part A. Sometimes I say part A, sometimes I say part 1, it doesn't matter which one you say. As soon as you are consistent. If you start from alphabetically, then you say A, B, and C. But if you start with the numeric number, say 1, 2, 3. Clear? So once we found, and now again remember, C equals n times n minus 1 by 2, and n is the number of links, and C is the number of instantaneous center we need to find. And then Kennedy's theorem, part 2, he said, hey, draw a circle, and that circle need to be segmented by the number of links, but not the number of ICs, number of links. And then by visual inspection of the mechanism, the instantaneous center that are known to you, you connect them. For example, if you know 1, 2, I12, you connect the I12 with the continuous line. And then unknown one, you will be finding by connecting other possible numbers. And that is called Kennedy's theorem part 2. Very important, I'll show you in a second. We will do an example now. And then to find the unknown instantaneous center, we have to use Kennedy's theorem part 3. And Kennedy's theorem part 3, it says that at any given line, straight line of radius of the instantaneous center, there should lie a minimum of 3 instantaneous center. Minimum of 3 instantaneous center. And using that principle, we'll be finding all the unknown radius of the instantaneous center. Unknown instantaneous center we'll be finding. And once we find all of them, we will collect some and to find the velocity that we need to know. So I have written everything very line by line. Look at here how I wrote. Procedures. At any radius of the instantaneous center of a straight line, there should lie at least 3 instantaneous center of zero velocity. That's the very fundamental part of Kennedy's theorem part 3. And I also write all these things very step by step, how you will be going using all 3 parts. You don't need to memorize, you just a couple of times you practice. Also you do your assignment, it will be already come to your head. Clear? Because if you try to memorize word by word, that is not a good thing. Absolutely not. You read it and then you will memorize try to say in your own words how you understood. Clear? Don't need to memorize. I'm also, if you ask me that to write it next time, I'll be writing slightly differently, but meaning will be still the same. Meaning will be still the same. So don't need to memorize line by line. You read a couple of times and then you try to understand what I'm saying. That's all. There are a couple of examples. Example 1, example 2, example 3. Example 1 and example 2 I will not go through. It's so simple and you can see it at home. I did everything very step by step. I will be going through your example 3 because example 3 is a very similar degree of difficulty as your assignment. So it will be giving you confidence that how you do your assignment, and to understand very basic simple one, you can also see this particular problem. Remember we did with the analytical approach of instantaneous answer, but graphically it will take only few minutes without doing any math or anything. Only you need a compass and a ruler, nothing else. So you do it at home. See, but I will do the other one now so that it will give you confidence, because otherwise we will not be able to finish all of the things that I want to do with you. Okay? So, and I put step by step. I will go I put only 2 examples. So that example 2. Let's go. Example 2. I just want to delete some of the things here so that it will not distract you. Okay, so anyone can tell me how many links we have in this mechanism? Hey young people, look at that and tell me how many links are moving.
6.
How many?
6.
Alright, this young man says 6 links. So I understood that he most probably means that total links. Right? Total links is 6. That's right. How many links are moving? Moving, it means
5.
one of the 3 motion, translational motion, rotational motion, or general motion. How many? 5. We have our link OA. We have our piston or a slider slides on link. Piston is actually link 3. Ground is 1, and then this links, which is link 4, and this link is link 4. And on the link 4, our slider slides on the link 4. Okay? And then this is not a slider, it is just a joint here. Clear to everyone? Because when you see half symbol of the slider, it is actually joint. It is not a slider. When you have slider or a piston, you see like a half. You see half, one section, other section not there. So it is a joint. It is a joint. It is not a piston or a slider. Nothing. So, and then our link 5 and this is again piston, and it slides on the cylinder wall on the horizontally. So that is our link 6. So this young man correctly said this mechanism has a 6 linkage total, including ground, and our 5 links are moving. Link 2, link 3, link 4. Link 4 is this one. Enter this length is the link 4, and then link 5 and link 6 has a motion. Clear? Out of them, link 2 has a pure rotational motion in relation to O, and our link 4 has a pure rotational motion in relation to D, and our piston, this one, the link 6 has a pure straight line motion or rectilinear motion we call it, and our slider 3 also has a straight line motion. Why it has a straight line motion? Anyone can tell me? Our link 3, why our link 3 has a straight line motion? Anyone can tell me these things? Because, look at here. This link 3 moves on link 4, correct? On the link 4, yes or no? But link 4 is moving, rotating in relation to point D, correct? Our link 4 is rotating like that in relation to point D. But regardless how our link 4 is rotating, it does not matter. Our piston at point A, the piston link 3 will be always moving on the link 4, and our link 4 is a straight line. Our link 4 is a straight line. So look at here. Our piston will be always moving like that. Clear to yes or no? If you consider my left hand is a piston, that point, that link 3, and my right hand is a link 4. So now look at it very carefully. Look at here. My link 4 is moving in relation to point D. Clear to everyone? And my piston, my left hand, and it will be moving. My piston is always on this line. Yes or no? So for piston 3 or piston link 3, piston always has a straight line motion. It is dictated by link 4. But link 4 has a rotational motion. That is other story. Clear to everyone? Is it clear or not? Because our piston is always moving. Look at here. If my link 4 is moving or not moving, my piston will be always a straight line path for piston. It will be moving on the straight line. Clear to everyone? Look at here, my finger is moving. Look at here. Look at here. It still is a straight line. Every section is a straight line. Clear? Regardless of position of link 4. That's what I say. That's very important thing. All right. Now, young people, how many instantaneous center we have on this particular problem? So, 15. This young man already calculated 15. Most probably he did it in his assignment, 6-bar linkage mechanism. He put his Kennedy's theorem part 1, C equals n times n minus 1 divided by 2. So therefore n equals the 6. We put it there, it will be 15. Is it? I think this young man calculated this mathematically this way. So we put here C equals n times n minus 1 divided by 2, and our is a 6-bar linkage mechanism, so 6 minus 1 divided by 2, and it will be 6, 5 times, that will be 5 by 2, so 30 divided by 2 equals 15. That's correct? Now, okay, now looking at the mechanism, hey, have a look. I think I need to go back to our previous problem to you understand a little bit. Let's go to our link, this one. The crank connector piston mechanism. Maybe it's too crowded. I draw it here and then you help me a little bit and then we'll move on to our 6-bar linkage mechanism. So look at here. Our crank connector piston mechanism, example 1, it was this one. Look at here, young people. Look at here, and this is the ground 1, this is link 2, this is link 3, this is the link 4, and ground, O, A, and B. I'm talking about our previous problem I'm going to. The process, how to find. So in this mechanism, we take it out, we don't need it anymore. So in this mechanism, here, our Kennedy's theorem, part 1 or part A, part 1 is a C equals n times n minus 1 by 2. And in our case, n equals 4, including moving and immobile links. Immobile is a ground. Total 4. So if we put it 4 here, so it becomes C equals 4 times 4 minus 1 divided by 2 equals 6. Correct? And then now by visual inspection of this mechanism, anyone can tell me, do we have any instantaneous center actually in this mechanism? Now, every joint in the linkage mechanism is also one of the instantaneous center. Why? Because I said, if the two links when connected together, if that joint point has the same magnitude of velocity belongs to both links, there is no relative velocity at that point between these 2 points. They have only one magnitude of velocity. Remember, at point A, at point B, at point C, the absolute velocity belongs to both links. So therefore, there is no relative velocity. That's why I actually wrote it. I'm not sure how many of you, I skipped that one, I don't explain to you very well. This one. That is our rolling point, no relative velocity at that point. That's why if the friction happens at that point, slip happens, that it is not instantaneous center. There is a relative velocity. Clear? And again the same thing. So therefore, we can consider in each of these links, and here we have at that point one instantaneous center because no relative velocity. At that point, at point A, link 2 and link 3 has the VA magnitude at that point. There is no relative velocity between them at that point. As soon as you are coming from that point, there will be relative velocity. Clear, everyone? As soon as you are coming away, as soon as at that point is your VA, and that VA at point A exactly belongs to both link 3 and link 2. If they are not exactly same, this joint will be disconnected. You will not be able to hold them together. Clear, everyone? But if you are moving away from that point, there will be relative velocity. We are not taking into account on that. That's why we are talking only at that joint point. So each joint point is one instantaneous center of zero velocity. So therefore, by visual inspection, we can write at least a couple of them. So let's go to find out how many of them we know. First of all, we know at point O, I1, 2, because this is a 1 and ground 1. The ground 1 and the link 2. Look at here, ground 1 is fixed and link 2 is rotating in relation to that. So therefore, that joint is a I12. Clear, everyone? There is no relative velocity there. And at point A, we have a I23 here. And then at the piston, and where piston and connecting rod is connected to the piston pin, at that point where I am holding with the laser, that point also have a I23. Sorry, not 323, 34. And then another instantaneous center we have. Well, which one this one? I12 at O, I23 at A, and I34 at connection point of the connecting link at point B. And then we also have I14 or 41. Why I have 14? Anyone can tell me? We have one more in this particular mechanism. We have I14. Where it is? Where? Because if say this one is rotating this way, angular velocity, omega 2, our VA, this is our VA, and our VB will be moving that way. So the VB on the radius of the instantaneous center will be, and it is that point. We are looking at that point because our link 4 sliding on the ground where? Our link 4 is sliding on the ground. This is our link 4 slider, and this is our ground 1. At that point, what is the instantaneous center of the velocity? Because it's a joint. Remember, it's a full joint. You said on the other day. Yes or no? It is sliding. We said full joint it is. The first thing, degree of freedom, we explained. Or primary joint. So at that point, because this is V is the mass center, correct? But on the surface of this one, what is the V? Is it different V of the piston? Or is the same V? Do you understand my question? This is our piston. This is the center, right? I showed the VB at the center here, VB. And now I am asking you, say we are here. I want to know on this, at the end of our piston, what is the velocity here? And at that point, what is the velocity? Linear velocity. It should be exactly the same. Otherwise, piston will be rotating. Get everyone? So, as you said, young people, it will be still the same VB. It will still the same VB and parallel. That's why it is moving a straight line path. Isn't it? So I am talking about that velocity VB with the surface of the cylinder wall at that contact point. What is our radius of the instantaneous center? At infinity. Why? Because our slider has a pure translational motion. Therefore, if it has a radius, that radius must be on this line somewhere. So therefore we call I14 at infinity. We must write. It is not only 1,4 at infinity. So now Kennedy's theorem says we have a 6, but by visual inspection we found 4 at infinity. At infinity. So now that's why Kennedy said use my second part of the theory. Now Kennedy says because by visual inspection we found 4, and by our Kennedy's theorem says we have a 6, 2 are missing. 2 are missing. Clear to everyone? And that's why Kennedy said use my second part. Kennedy does not say you to use arbitrarily. And what he said? To find out. And now if I ask you, okay, there are 2 missing, and if I go, say 2 people are missing from somewhere, and I go to policeman, if I say, hey, well, police officer, our 2 people are missing, and what the police officer will ask you? Hey, young people, if you go to the police station and say, I have a lot of people, out of them 2 people are missing, I don't find where they are. So I need your help to find them. Correct? So what the police officer will ask you? Tell me, it's all dynamics in the real life. What the police officer will ask you?
What they look like?
Exactly. They will say, okay, they are old people or young people. How they look like? Did they have any outfit? Do you remember their color of the dress or something? Did they have any luggage? I'm giving an example. This young man is 100% correct. How they look like? So that based on that criteria, the policeman will be going to look for. Otherwise, policeman will be spending a lot of time, no clue where to look for. So that's why Kennedy said, the 2 are missing. We found 4. And Kennedy said, I will help you using that theory. Part 2, you draw a circle. He said, draw a circle. A circle. And the circle segment by the number of links, not by number of instantaneous center, by the number of links, n. So how many equal? So how many of them? 4. So we do it here. 1, 2, 3, and 4. And then he said, in his part 2, he said, connect this number that you know by visual inspection with the continuous line. So what do you know? Connect this number with the continuous line, which you already found by visual inspection of the mechanism. So we found I12 at point O, 23 at point A, 34 at point B, where is the connecting rod and piston connected with the piston pin, and I14, which is the contact point between the surface and the piston. So we write here I12 we know, we connected here, and then I34 we connected, and then I34 is this one, 2, 3, and then I14 we know. And then Kennedy said in his part 2, try to see, is there any other number you can connect? Try to see, is there any other number you can connect? we can clearly see, we can connect I13, and we can also connect I24. And now I am going to police station, as this young man correctly said. I am going to the police officer and say, hello officer, I missed 2 people and their name is I13 and I24. Then we can find out. Police officer will go for, ask the name, hey, what is your name, document, all this, and so on. Exactly the same thing. That's the Kennedy said. Kennedy said you cannot find an instantaneous center arbitrarily if you don't know which one you are looking for. And we are looking for 2 in our 4-bar linkage mechanism, I13, I24. So our unknown is I13 and I24. And now unknown, total 6. Can you see that? Do not arbitrarily do something without knowing what you are doing. There is a reason for that, how we are doing. And then now, we already identified, we know which one we are looking for, and then we will be using Kennedy's theorem part 3. Kennedy's theorem part 3 is helping us to find the unknown instantaneous center. That's why he said that you at any given radius of the instantaneous center of zero velocity, on that straight line there should lie at least 3 instantaneous centers. And that's he said. After that he also paused. And then he said, but it is a very vague statement. At any straight line there is at least 3 instantaneous center lies. It does not say very concretely what are the things actually we need to do. Then he said that you select from your this circle 2 triangles such a way. Again I am repeating. Kennedy says in part 3 that from here you select 2 triangles such a way, and those 2 triangles only one side is a common and unknown. You cannot take 2 triangles from here which more than one side is unknown. Clear to everyone? So in this case we can take 2. Look at here. If we want to find I13, we can take 2 triangles. 1, 2, 3, 1, 1, 4, 3, 1. If we take these 2 triangles, our I13, that's a common and unknown, only one side. Clear to everyone? And for I24, we can take the top 1 triangle. Look at here. 1, 2, 4, 1, and 2, 3, 4, 2. Our 2, 4 is common for these 2 triangles. That's how you will be selecting the 2 triangles such a way so that you can find the unknown instantaneous center. Clear to everyone? That is a part 3. It is not I am saying, it's Kennedy saying. Okay. Now we are going to our 6-bar linkage mechanism. All right, young people, very crowded. In Melbourne, usually I draw it on the board, one step by step. But here, if I do step by step, it will take a little bit time. So we cannot go all the details, but I will try my best to explain you how we are getting it. So at the moment, don't worry about this crowded thing. First, we need to focus in Kennedy's theorem part 1, and then part 2, and then part 3. And I give you a little bit of help where you need to focus, and then where you can have a little bit less focus. Clear to everyone? That is my objective here. So now is a 6-bar linkage mechanism. So using our Kennedy's theorem part 1, because let's go, we'll have around say, what's the time now? Because my time is the Melbourne time. 3:20. Oh, we have a watch. Oh, okay. The watch is at 3:25. Let's go. We will stop around around say 350. Is it okay?
Okay.
So now young people, our plan is 350, we will stop for a short break. So during that break, those who are already sleeping or only 10, 15, 20 minutes you are taking nap, you wake up. Clear? And after that, we will go to the new topic. So this topic I try to finish within around 20 minutes, 25 minutes, okay? All right, now let's go. Hey young people, let's go to see. At the moment, don't focus on the left hand side because it will confuse you. I'll do with you one by one. So now, our first part, Kennedy's theorem, and the idiot way, because every time I write from my head, I could not remember what are the things I have written before. You got my point? So that's why you will find somewhere step 1, step 2, step 3. Somewhere you will find the part 1, part 2, part 3. Somewhere I say part A, part B, part C. Clear to everyone now? So you forgive me for that because unfortunately I am not memorizing anything. I am writing every time but the same thing, not slightly different way. So now the first thing we'll be doing, this one you also have done in your assignment, the Kennedy's theorem part 1, C equals n times n minus 1 divided by 2. As you unfortunately know that we have a 6-bar linkage mechanism. So therefore when we put 6, unfortunately the number becomes 15 total. Now remember, in 4-bar linkage mechanism, current piston mechanism, we found that 6 instantaneous center. 4 by visual inspection we found, and 2 we found unknown. That is using Kennedy's theorem part 2, we identified who they are. And now have a look here. We have a 15. How many links increased? 2. In a 4-bar linkage mechanism, IC was total 6, and our 6-bar linkage mechanism, IC is total 15. If you increase our 8-bar linkage mechanism, young people, you can look at their number will be significantly bigger. So as you increase more and more, our complexity will be more and more. The graphical method will solve you and help you with this. Analytical method will not be able to. So now have a look. By visual inspection, let's go to find it. Don't look at the crowded thing. We go our previous slide. So it will be easier for us. Previous slide. Now, our Kennedy's theorem says we have total 15. Let's go to find, looking at, I also numbered them, it will be easy for you young people. Each of the joint, I help you a little bit so you understand. Each of the joint is an instantaneous center. At that point in the instantaneous center, we have no relative velocity. At that point in the instantaneous center, also we don't have a relative velocity. And our link 2 and link 3 is connected at that point, also in instantaneous center. And link 3 and link 4. Hey! Link 3 and link 4. Now for link 3, it is sliding on link 4. It is almost like our cylinder wall. Clear everyone? For link 3, it is sliding. Link 3's path is dictated by the link 4. Clear everyone? As our linkage mechanism, previous one, or maybe here, as the path, how our piston C will be moving, right or left, who dictates? Who decides it? The cylinder wall. Cylinder says which way our piston will be moving. Yes or no? Correct? Okay, so here our link 3, when it slides on link 4. So therefore, for it, our link 4, for its motion, link 3 in relation to link 4, it is a translational motion, and its direction will be either this way or that way. Therefore, radius of the instantaneous center will be at infinity, but perpendicular to that link. Perpendicular to that link. It can go this way, it can go this way as well. Clear everyone? And then link 4 and link 5 at point B, and the link 4 and ground 1 at point D, and then link 5 and link 6 at point here. and then being 6 at the contact point with the ground cylinder wall is another one at infinity. Because our velocity is going this way, the radius will be at infinity like that. Correct? So how many of them we found? Let's go to number them. Let's go to number them. I12 at point O, I23 at point A, I34 at infinity perpendicular to link 4, and then I45 at point B, and I14 at point D, and I56 at that point, and I16 at infinity, which is our cylinder wall dictate. So therefore it is the horizontal axis, our velocity, and our radius of the instantaneous center at infinity. It is going not only up, it is also equally is going down. Clear to everyone? So if I see some of you showed your in your assignment, you showed your radius of the instantaneous center, the dotted line, only going up, it is not going down, then I can consider you are a superhuman. Otherwise, how do you know it is going to the right? Because our velocity is going this way or that way. Is a translational motion. Our radius of the instantaneous center will be on this line anywhere at infinity, up or down. Is it clear? If I do not see that dotted line is going this way, I can say, oh my God, finally we found a superhuman. Okay? Grammar. Need to follow the rules. I know all of you in Singapore, those who are Singapore national, you also do a little bit of army training. Isn't it? Left, right, or something. And also maybe shooting as well. But shooting, we are not, with peaceful people, we are not going there. We focus on here. So what you did there, the whole purpose is discipline. That is the main thing. It is not the shooting, it is the discipline. Okay, exactly in our case also we need to be following discipline. That's all. Alright. So how many of them that we found? 1, 2, and then 3, 4 is an infinity. Another one, 4, 5, 6. Oh, the one is more increased. 1, 2, and 3, 4, 5, 6, and 1 at infinity, 7. But our radius of the the Kennedy's theorem says we have 15. So it means 8 unknown. Our life is significantly harder compared to the formal linkage mechanism. So what I need to do now? Of course, Kennedy's theorem part 2. And Kennedy's theorem part 2, we will draw a circle, and that circle need to be equally segmented. You don't need to exactly equally do it. You can do by hand. But as soon as you are more or less equal. Clear? So, there you will be segmenting by the number of links. And how many links you have? 6. So, that's the things I did here. I took, look at it very carefully. I took a circle. I did not use any tool, any instrument. Can you see that? How do you know that I did not use any instrument? Anyone can tell me? How do you know that I did not use any instrument? I draw it by hand. Why, young man? Yes, there will be, because our hand, our body is vibrating around 2 hertz per second, every one of us. Maybe some of you a little bit more, some a little bit less, but close to it. That's called our natural frequency. Everybody, human being, or any object, if they have a stiffness and mass, they will be vibrating. That is called natural frequency. The formula you learn. F equals square root of K by mass. Stiffness divided by the mass. If any object has a stiffness and mass, they will have the vibration. Clear, everyone? And that is called natural frequency. And if you divide by that formula, 1 by 2 pi, it will be hertz. If you put there, now at the moment it is a radian per second, young people. If you put 1 by 2 pi, it will be hertz. But I don't write that things, because I only try to remember only one type. Other thing automatically I write later on. Okay, now, young people, so in our engineering drawing, we need to do 2 ways. So you can draw this one, as this young man correctly said, when our human being is moving. So when you draw this one, line will be little bit not straight, okay? It will be little bit offset. So that looking at that, you can immediately say the handwriting. So now, look at here. We segmented 1, 2, 3, 4, 5, 6. And then we know 1, 2, look at here. By visual inspection. Can you see that? And I beautifully want to see in your assignment all those nice words that I have written here. How you got? By visual inspection. I did not bring from Melbourne. Those I1, 2, I3, I4, I5, I did not bring from Melbourne. All of them I found with you with the visual inspection of the mechanism. Clear to everyone? You need to write it from where you got it. So 1, 2, we connect continuous line. 2, 3, we connect continuous line. 1, 4, we connect this one continuous line. 4, 5, we connect. But in your assignment, link 4 and link 5 has no connection. Link 4 and link 5 has no connection. So in your assignment, that will be dotted line. Clear to everyone? But you have link 3 and link 5 connection. This one is a continuous line in your assignment. Principle exactly the same. No difference whatsoever. And then I5, 6, I1, 6 at infinity. That's all. And now we are using Kennedy's theorem part 2, the second section. And he said, connect all other possible number. That will be your unknown instantaneous center. So look at here how I do. Hey, I first connect I13. But of course, as we don't know, we put a dotted line. I13. And then look at here how I do. I flip over. I go I15. I did I13 and then I15. I just mirror image on the other side. Clear to everyone? And then I went to, after that, I went to this one. I went to this one and then, so 1 second, also my apology. Yeah, this one. 4, 2 and 4, 6. Again, I flip over. 4, 2 and 4, 6. Clear? These first 4, you need to follow discipline when you also determine them. Thereafter, you can be indisciplined, not a problem. But if you don't do it, you will have a problem. This particular problem. So, 1, 3, 1, 5, unknown. And then 2, 4, 4, 6, unknown. And there are also some other left. 3, 6, 2, 5, 2, 6, 3, 5. In your assignment case, 3, 5 is a continuous line, but 4, 5, 4 or 4, 5 is a dotted line. That's all. Clear to everyone? And now we figure it out. I13, how many of them? Actually, 8 of them. And now we go to Kennedy's theorem, part 3, to determine that all the 8. So as I said, we will be following the discipline first. I13, look at here again. I13, I15 next one, and then will be I24, and then I46. Easy to remember. It is not a problem at all. Every one of you, look at there how it is a discipline. And thereafter you can take any combination on if it complies that 2 triangle, one side common and unknown. That's all. Okay, so let's go to we start our main business here. So first thing, and every time when you draw it, you also take these two triangles. Look at here, go back to here. We are taking, our first objective is to find I13. Look at here, I13. If I13, we are taking these 2 triangles, 1, 2, 3, 1, 1, 4, 3, 1, and 1, 4, 3, 4 is known to us, and 1, 3 is unknown for this triangle. And then 1, 2, 3, 4, 1. 1, 2, 3, 1. This is common for other triangle, and 1, 2, 2, 3 is known to us. That's all. And that's the things I wrote here. You see how I showed? Why we did it? Because so that we are not confused with the other line. That's the only reason, nothing else. So now we need to find it. Let's go to find it. I12. In one side we have I12. I12 is at that location. Can you see O? And I23 is at that location at point A. So it means our beautiful I13, this I13 is located either between O and A or beyond A or beyond O on this line. Clear to everyone? Now look at here again, I'm saying what I'm saying. I said, looking at my I12, 2, 3 and 1, 3, looking at that triangle, I determine that I12 is at point O and I23 is at point A. So it means our I13, the other side of the triangle, is located either between O and A in this line somewhere, or beyond A or beyond O, but on this dotted line. Clear? And that's why I put a dotted line here, and I also continued dotted line there. But I did not continue too much, otherwise it will be too crowded. That's the main reason. Is it clear? But I am not still sure exactly where is our I13. But I already identified that it is on this line, somewhere. Either between A and O, or beyond A, or beyond O. That I already can say, even looking at one side of the triangle, as per Kennedy's theorem part 3. And then I am moving to our I14, I34, and I13. 1, 3 we need to find. So let's go to see I14. Where is our I14? I14 located at point B. I think this symbol and your schematics, maybe that B are not the same location. I think we said different. So please check it. Clear to everyone? So here, at point here is our I14. Here is I14. And our I34 at infinity, it is going this way. You can see I put a little dotted line also downward, but I did not continue too much because I don't want it to make it too crowded. Clear? So, unfortunately our I13, not I13, I34 at infinity, it is passing through point A, but our I14 is here. I14 is here. It is not the same location. And now remember that point. Any radius of the instantaneous center that is at infinity, that can parallelly move at any location as many times as you want. And our I16 at infinity, this one, we can move here, we can move here, we can move here, we can move here, but parallel. Only the radius that is at infinity, that one. But we cannot change the angle. Is it clear? So what we did? I13 at infinity, I am now bring it to put it on I14. And our I34 at infinity, it means on this line, it could be anywhere. But Kennedy doesn't say exactly where. He said that on any straight line should be 3 instantaneous center, is it? So we assume it is on this line. So we have I14 here, and on this line we have a I13 somewhere. On the other hand, we have this line, somewhere I13. Where these two lines intersect, that is our I13. Clear to everyone? Where this line, this black dotted line and this red line, and you always remember the same color, because here I put the red color, you also put the red color. And also write again 3, I34 at infinity. That's what you need to write every time, because otherwise you will be confused. But if you do not write I34 at infinity, the word at infinity, it is absolutely disaster. Absolutely disaster. It cannot be with other instantaneous center which is not at infinity. It's two different things. You must write it. Every time you move, every time you write. Look at there, how many times I move? Every time. Look at there. Original position here, we copy it, we put it here, we put it here. And every time I'm writing I34 at infinity, I34 at infinity. Clear? So we found our first instantaneous center. And now we move on to our I15. So when we take I15, we'll be taking this triangle, I16, and the 5, 6, and I15 here, and then I45 and I14, and on the other side, this one is the common. So now let's go to see I16. Hey young people, I16 is here. Can you see? At infinity, passing through point, that particular point as well. I think I showed you in the schematics, this is C. So my apology young people, because every time I write something, I do not necessarily look at what are the things I wrote there. But it is essentially, the main thing is the link. Link number need to be correct. So I16 here, I56 where? I56 is at point here. That's the joint point where our link 5 and our piston is connected with the piston pin. Clear to everyone? So therefore on this line somewhere is our I13. Sorry, not I13, 15. And then we move on to the other side, I14. I14 is here. Hey, look at here. I14 here. And I14 and then I45. I45 is at that point. Clear to everyone? So it means our I15 should be between B and C or beyond B or beyond C, parallel to our link 4. So what I did, I dotted this line here and I continued, and where it goes here, that's the beautiful I15. Here. Here is I15. So what do you do? Every time when you take the next one will be, most probably we will take this one. Look at here. Look at here. If I take our next one is a 2, 4, we have to find. 2, 3 we already know. 3, 4 we already know. On the other side, other triangle 1, 2 and 1, 4. And the other one is a common. Clear to everyone? So let's go to take that one. I24, if we want to find, it will be 2, 3. What is our 2, 3? 2, 3 is at point A. Link 2 and our piston at point here. And then I34 at infinity. Okay, what a bingo. It is already on that line, that point. So we don't need to do anything. We don't need to move anything. So again, look at here. I23 is at point A and I34 at infinity passing through also point A. So it is already there. We don't need to do anything. And then on the other side, we have a I12. It is here. Look at here. It is the I12 here. And then we have which one? I12 and I14 at infinity here. So what do we need to do? We just move that line, we connect this because it is in between 1, 4 and 1, 2, or it can be beyond B or beyond our O. So I am drawing that line, and that line where it intersects, that is a beautiful I24. You are with me or not? If you are not, tell me, please. I am here to help you. I do not want to rush until you understand it. So if you don't understand, don't feel shy. Ask me, I'll repeat it again. Clear? So again, I think some of you are looking at me, so most probably not very clear. Look at here. Unfortunately, the triangle that I took, it is on other page. I cannot see it. That's why always young people, where you take the triangle and your schematics need to be next to it, then you can see it very nicely. Clear? Because our schematics is here. Look at here, 1, 5 and 2, 4 I am talking about. And the 2, 4 is this one, not this one. 2, 4 is this time. 1, 2 and 1, 4. And the 2, 4 is the common we are looking for. And on the other side, 2, 3 and 3, 4. And 2, 4 is a common. That's the thing. So our 2, 3 and 3, 4. 3, 4 is a line at infinity. So that is our here. Our 2, 3 is here at point A, and our 3, 4 at infinity, that line, that red line, original line. They are in the same. And then our 1, 2 is here, and our 1, 4 is here. So our I24 will be either beyond B, between O and B, or beyond O or beyond B. So that's why I'm connecting this dotted line all the way up to that point and downward, and we see that line intersects with here. So that's why it is our I24. Clear? And the next one we'll be taking 4, 6. Look at here, 4, 6. And another important thing which I did not mention. When you found, say we found 1, 3, remember? And then it make it continuous line. After you getting it. Once you get it, you make it, this you don't touch it, this one. You draw another circle. And that one you use, which one you found, gradually you make it continuous line. from. So 1, 3 we found continuous line, 1, 5 we found continuous line. Clear? Dotted line, make it continuous. And we found 2, 4, make it also continuous line. And then we'll be finding now 4, 6, also will be making continuous line. Then it will be easier for you to select other triangle which you can find two triangle common unknown. Clear to everyone? Otherwise you will make it a disaster. That is the process for the instantaneous center of zero velocity to find it. So now our 4, 6, look at here, 4, 6, hey young people, look at here, 4, 6, we have a 1, 6 at infinity and 1, 4. Hey young people, 1, 4 is at point here. And where is our 1, 6? 1, 6 passing through that point at infinity, going up, going down. You can see that line. Can you see? And I have also written I-16 at infinity. Can you see that on the top? But this I-14, it is a fixed line. I cannot change it. And this one, as I said, we physically can move. We move it and we put it here, passing through I-14. And I am writing that beautiful line somewhere. I also wrote I-16 at infinity. Can you see that? So on this line, it is there. And then we move on to other side. We have a 4, 5. What is our 4, 5? 4, 5 is here. Link, this is a link 4 and this is link 5 here. And 5, 6 is here. So it means our 4, 6 will be either between that point and that point, or beyond that line, or beyond that line. So what I did, I just connect them. The 5, 6 here. I just connect them, and luckily it coincident point it comes here. Clear to everyone? Depending on your geometry in your assignment, that point can be, it can coincide with other point, or it can be little bit below, or it can be little bit up. You don't need to worry about that. It is whatever your geometry is giving you that point. And after this 4, you can be in discipline. So remember, first we try to find I-13, then you try to find I-15, and then 4-2, and then 4-6, which we found now. Clear? And then you make them continuously. And then you look at other 4, which triangle combination you can take so that you can get the unknown instantaneous center. That's all. If you do not follow this first 4 discipline, it will be extremely hard for you. Alright, next. Next, I followed this sequence. Look at here, 5, 6, 7, and 8. You can try in different sequence. Clear to everyone? This is I did at home. So our I-35, 3-6, 2-6, and 2-5. That's the last 4. I took that sequence. For 3-5, look at here, where is our I-35? 3-5 is this one. 1-3, 1-5, and 3-5 is the common we look for, and 3-4 and 4-5. So let's go to, now young people, you need to help me a little bit. Because 1-3 and 1-5, it means, where is our I-13? It is a fixed. 1 it means ground. I-15 is also ground. We cannot change them. We cannot move them. So let's go to C. It means our I-35 belongs to between I-13 or I-15 or beyond I-13 or beyond I-15. So let's go to C in our schematics quickly, because we are running out of time. We are running out of time. Just 1 second, we quickly need to go. So I-15 is here, I-13 is here. Look at here what I did, young people. Our I-35, this 3-5. Look at here what I did. This 3-5. We want to find this one triangle 3-4, 4-5, 3-5, and then 3-1, 1-5, and 3-1. Because 1-3 we already found and 1-5 we already found. So it is a continuous line. Clear to everyone? That's why I told you to make a continuous line. Otherwise, it will have a confusion to you. So now, our 1-3 is here, 1-5 is here. So it means our 3, 5 should be between 1, 5 or 1, 3 or beyond 1, 5 or beyond 1, 3. And that's why what I did, young people, look at here. I draw a different color line. Can you see that? Dotted line. And that dotted line I put, not only connected these 2 points, 1, 3 and 1, 5. I also extended both sides. I left it here. And then other side, we have a 3, 4 at infinity. Look at here very carefully. 3, 4 at infinity, which is located at this one. This one. At infinity, it also go down as well. And then other side is the 4, 5. What is our 4, 5? Is here. Look at here. 4, 5 is our link 4 and link 5 at that point. But 3, 4 at infinity, it is there. It is not the same location. So what I did, I bring this one, it here. I put it again there, and then I put also side 3, 4 at infinity. I brought it parallelly. And therefore, this line and this line where it intersects, that is our I35. Clear to everyone? I'm not doing any different thing. And then of course, we follow the other one. Next one is the 3, 6, correct? 3, 6. 3, 6 is this one. 3, 6 is this one. 1, 6 at infinity, 1, 3. 1, 6 at infinity and 1, 3. 1, 3 is on the left hand side and 1, 6 at infinity at passing through the piston. Remember there? So we need to bring it to put on I13. So let's go to see. Where is it? I13. So what I did, I13 here, I16 is here. So I brought it, I16, I passing through, and you can see clearly, I show a dotted line downward, I show dotted line here. And on the top, again I wrote it, I16 at infinity. Is it clear? I brought this one in there. And the other side, let's go to see, I didn't look at the diagram. The other side is a 3, 5. Other side is a 3, 5 and 5, 6. Look at here again, 3, 5 and 5, 6. 5, 6, 5, 6 at the end here. And 3, 5 we found few seconds ago. So let's go to find it. What is our 3, 5? 3, 5, few seconds ago we found here. This one is 3, 5. This one. And then here is the 5, 6. So what do we need to do, young people? What do we need to do? We need to connect beautifully through the other line, and then where this line is connected, that is our 3, 6. Is it clear? And we can find subsequently. So which one are you looking for now? The next one, let's go have a look. We are doing 3, 6. Sorry, 3, 6. We are looking at 3, 6. So 3, 6, we have a 3, 5 and 5, 6. Let's go again. What is our 3, 5? 3, 5 here. Can you see that? Hey, 3, 5 we found few seconds ago. And 5, 6 is here. So we draw a line, and that line continue, and our I16 at connected here, that is our 3, 6. And 2 more. And 2 more, and then we will stop. Last 2, 2, 6. 2, 6 is our this triangle. Look at here. Now the recipe for doing the instantaneous center, finding all the instantaneous center, the main recipe is every time you found the right one, immediately make that line continuous in your circle. Clear to everyone? Then it will be easier for you to find which 2 triangles you will be selecting to find the other unknown. So now we want to find I26. I26, I12 and I16. I12, we know that I12 is the initial location and I16 is extremely right. So let's go to have a look. I12 at that point here and I16 here. So we need to bring it here.